Alrighty. So, as Mr. Dersh said, I am a history of math student, and in the first few weeks of our class, we ended up learning about the Pythagoreans. And way back in, I remember Calc 1, I remembered hearing that the Greeks didn't think 1 was a number. And that just really got me kind of confused. I had a bit of a crisis. I didn't understand what was going on, and that's when I got interested in the Pythagoreans. And it took a while, but 2 years later, here I am actually being able to give a presentation on them. So, math hippies. This is a math seminar, so I'm assuming you folks are here because you like math, and if you don't, please just don't tell me, and we'll all be all right. So, question I have for you is, do you think that you have what it takes to be one of these Pythagoreans, to be a math hippie? Most of us are already math people, so let's see. All right, can I ask everyone to put your hand up? All right, take your hand down if you don't think you could deal with the requirement or the suggestion. So first one, only ever wear white for the rest of your life. All right, okay. Avoid beans, okay. Be a young aristocrat, you don't have to worry about this one. Abstain from alcohol. Have no personal possessions whatsoever. This is kind of the hippie vibe. They all shared everything. Everything was communal. They all, what's mine is yours, what's yours is mine. We got one standing. All right, go Sam. Live only to study. No, okay, all right. The next one I think is the hardest one for me personally. They could only listen to the master's teachings without question or input. They couldn't say anything at all for 3 years. And then only if you were deemed to advance after perhaps waiting for 3 years of your life, you could only advance if you're deemed worthy. So that's why I struggle with. That's a whole list of requirements. That's a whole, everyone's hand went down. Do you think you could pull it off? Apparently not. We had Sam, last one. All right, there's more actually. The Pythagoreans' nearby neighbors actually would put on plays and ridicule the Pythagoreans. They would call them dirty vegetarians who were actually scared of beans. They were also labeled as enemies of the new budding democracy because of their hierarchical structure, and their homes and meeting places were burned to the ground. So if their personal requirements weren't enough, the societal issues, it would be really tough to deal with. But these people cared so much, they still were part of this. All right, disclaimer. These people did exist thousands of years ago, and what we do know about them was written generations after they existed. So what we do have of them, what little we do have about them, is super conflicting and a whole bunch of myths and stories. We're not really sure what was going on. Also, there's no guarantee that my pronunciation will be correct. I might stutter on some of the many syllable words, but please just bear with me. All right, so let's get started. It all began in an area called Ionia, and in the era of classical Greek civilization. As you probably know, there are many Greek gods, and they believed that the physical world was explained by the wants and the acts of these many gods. In this era, they moved from this idea of mythos to logos, logic, that the world around them was explained in a logical fashion. This changing of worldviews was encompassed by the Milesian school of thought. The founder of the Milesian school of thought, I'll get back to that in a second. So, in other words, to explain the world around them, in this logos, they had a methodical cycle of inquiry and rigorous corrective intellectual processes. So instead of just accepting things from the heavens, they would have data, learn, make hypotheses, and we can start to see the beginning of the scientific method in this. The founder of philosophy and of the school, Milesian school of thought, Thales, was the first of 7 wise men in Greece. He was also a statesman, entrepreneur, engineer, astronomer, and a mathematician. He actually showed the people how to calculate the heights of the Great Pyramids using similar triangles. And most importantly, was the first to search for a logical foundation for geometric theorems. And by that started a primitive idea of proof. I don't know if in your math classes you've started to talk about proofs, but they're one of the biggest mathematical foundations for what we have today. Pythagoras was largely influenced by the Milesian school of thought. He was a mystic, philosopher, prophet, and geometer, and this is where the whole we don't really know what happened thousands of years ago come in. He might have been a student of Thales, personally, during his travels, but we don't know. What we do know is that he was definitely influenced by Thales' school of thought. One of the well-known things about Pythagoras is that he did travel around the world learning about numbers, music, and mystical rites. He definitely traveled to Egypt, and he definitely traveled to Babylon. He did end up having to flee his birthplace because a tyrant banned him because he was a very political entity and caused many controversial ideas to be thrown out there that people of more traditional thought didn't really enjoy. He was also rumored to have married one of his cult members. Another one of the things we're not quite sure about. Pythagoras founded the Pythagoreans, finally. So this is what we're here for. Where did he found them? In a bustling seaport in what is now southern Italy called Croton during the late 6th century BC. The Pythagoreans were a religious or a philosophical society, or as some books say, a mystery cult. And here we have a picture of them all wearing white and measuring things in the sky. When I looked up Pythagoreans, this was the only picture at all that really showed up, just in different sizes. Alrighty, so how were the Pythagoreans structured? How did they go about this? The Pythagoreans had two classes. We'd have the first class, which I kind of talked about in the do you have what it takes to be a math hippie. They were the listeners. They were considered the lesser mathematicians. Pythagoras had them represent the religious and mystical side of his schools of thought. They had to listen in silence to the master, never question the master, and they didn't ever really hear the whole story, the whole proof. They would hear bits and pieces. It would be brought down like religion. Whereas the mathematicoi, I'm guessing that word sounds familiar to you, were the more scientific side of Pythagoreans' thoughts. They did the actual research, heard all the full master's teachings, and they could actually express their own opinions, although they could not be published as their own. Everything was under Pythagoras, which is why a lot of things are attributed to him, even though we don't know they might be somebody else's. The mathematicoi actually included 28 women, not women's, sorry. One of them actually ended up marrying Pythagoras, and we do have a name, Thanos, and we don't know whether that name is for Pythagoras' wife or the child. So again, we have a name, but we don't know where it goes to. All right, so how continued? What did they study? What did they care about? So they cared about 4 things: mathematica, or arithmetic, geometry, harmonia, music, and astrologia, astronomy. Later in the Middle Ages, this was called the quadrivium. I don't know if you've heard about that, but even now that influences some schools. They believed that all of these things were connected and could be explained using numbers. The real question here is why? Why did they isolate themselves? Why did they follow all of these rules? Why did they bother? So, their ideology. What most distinguished the Pythagoreans from the other mystery cults of the time was their belief that the elation of the soul to unison with the divine occurs by means of mathematics. In other words, they believed all of these physical things in the world, if studied and understood, could be morphed into one thing, math. And by understanding that, they would have elation to the divine. All right. So trippy thoughts, layers of life. The Pythagoreans believed that they had the physical world, the world that everybody sees, everybody understands. And underneath that is the geometric world. I don't know if you've heard about the existence of a perfect circle. Does a perfect circle actually exist? Unless you talk about like the radius of a hydrogen atom, we don't really know. It doesn't really exist, but it exists in thought. If we can talk about and describe it, just like other geometrical shapes, it exists. So they believe that this was a plane of existence under the physical world. And then, under the geometrical world, they believed counting numbers was all. Counting numbers were the basis for everything in the geometric world and thus the physical world. They believed they could bring and collapse everything down to the counting numbers. All right, so that was some pretty heretical stuff, a pretty strange way to view the world. But some good does come of this. This belief that only using these divine building blocks of the counting numbers to understand the entire universe created pure mathematics and also gave way to the notion of formal proof. Instead of just saying, this is the way it is because we did a couple tests. We had to show it. We had to be true all the way through. A distinction should be made here. I don't know if you know the difference between applied mathematics and pure mathematics. Applied mathematics is basically the practical stuff, the stuff you'd want to use if you were building a bridge, if you're going to be a secretary, an actuary, the stuff you need to live your life. Whereas pure mathematics is the abstract stuff, in my opinion, the more interesting stuff, where you're studying to develop the principles of mathematics because it's math and because you see something in it, more so than for immediate use. So they were also making this transition. They called applied mathematics logistica, and they started to move to arithmetica. And something interesting to note here is that the social connotations of arithmetica have changed since that time. Now, when we're talking about a lower level math or applied mathematics, we might say, oh, that's just arithmetic. Whereas back then, arithmetica was the higher mathematics, where you were just playing with the abstract concepts, not building a bridge. All right, so a little bit more on the arithmetica. So the Pythagoreans strongly believed in the power of numbers, number mysticism. They believed that each number had special mystical properties that could be associated with human attributes or abstract concepts. And eventually, this number mysticism later split into numerology and number theory. Numerology isn't so scientifically based, so that's the more mystical part of it, whereas number theory does have a basis. A more reputable source, Aristotle, provided us with some of the Pythagorean number associations in his work Metaphysics. And I was just wondering if you guys think you could guess some of them. So numbers 1 through 4 have 3 parts. They have an abstract concept, an element, and a mathematical object, whereas number 5 just has one abstract concept. All right? So for number 1, do we have any guesses?
Lonely.
Unity? Lonely?
You gotta be hippie, you know?
Oh.
The loneliest number.
Fair enough. Yeah? Okie dokie. So it stood for reason, because reason leads to one truth. The element was Earth, and the mathematical object was a point, so just one singular point. And this is what got me interested in the first place. They didn't think 1 was a number. They thought of 1 as a unit. And when you have several units or a number of units, that's when number begins. And that just kind of blew my mind, and I still think that's one of the strangest things. But now I can accept it, and I've moved on. All right, 2, any guesses? Mathematical object, element. Balance? Okay. And, all right. Water? Okay. All right. Wind, so it's still kind of blue. It stood for man and opinion, air, and the mathematical object was a line. So, strangely enough, even numbers after 2 are feminine, even though 2 itself stands for man, because they are unstable around a center. And when I first read that, I was like, what do they mean? It means if you have like a table and it has 4 legs, if one of the legs is shorter, it would be unbalanced and uncentered, whereas if you had 5 or 3 legs, it could be balanced. So that's what they mean by unstable around a center. All right, 3. Maybe you can see a pattern with mathematical objects.
It's a triangle.
Triangle? Okay. It's a surface. So can see a trend. So you go from a point to a line to a 3D surface. It stands for woman in harmony. The element was fire. And flip of number 2, odd numbers after 3 are masculine. So odd numbers are masculine, and even numbers are feminine, even though 2 stands for man and 3 stands for woman. 4. Water. All right. Volume. Okay. Okay. So it's for justice, water, and body or volume. I say that counts. And the 5th one, I don't know how this one will go. Because I didn't think. I guess it made sense after I read it, but that's an idea that comes later in a second. So you're onto something. Okay. All right. So it stands for marriage because it's the sum of the first feminine and this first. Yeah, I guess that makes sense, but like I wouldn't have been able to pull that out if I had. Alrighty. So this is kind of the idea you were talking about. The sum of the first 4 numbers, the first 4 elements, the first 4 mathematical concepts can be moved together to create this perfect triangle, sum of 10 dots. They called this the Touchet Tractus, and it was used in oaths and prayers. They thought this was the perfect symbol, the number of the universe. Another symbol they used was the pentagram, and they used it for other communities of Pythagoreans to recognize each other, and this was a more secretive symbol. Some more stuff about the tetractys. They considered the tetractys to be its own realm of perfect number. You might have already heard of perfect numbers, but the type of perfect number you've probably heard of is the second type of perfect numbers, where an integer is equal to the sum of their proper divisors. An example of this is 6. 6 is divisible by 3, 2, and 1, and is also its sum. And we can see the pattern going on and on until I stop typing out all the divisors, because that would just go across the screen and not be very pretty to look at. Euclid actually came up with a formula for perfect numbers. So if 2 to the n minus 1 is a prime number, so 2, 3, 5, 7, so prime numbers, then 2 to the n minus 1 times the quantity 2 to the n minus 1 is a perfect number. And here we can see these first 4 I had on the other slide, and they were able to compute numbers all the way up there and say that it was, in fact, a perfect number. Amicable, or friendly numbers. 2 numbers are considered amicable if the sum of their proper divisors is of the, if one is the sum of the proper divisors of the other, and vice versa. So if I add up all the proper divisors of one number and get this number, and I add all the proper divisors of this number and get this number, it's considered a friendly number. In all honesty, these aren't really useful in modern day number theory, but they are considered an interesting introduction to the idea of it. Side notes. Okay, no, first. They only discovered 2 friendly numbers, 220 and 284. And why did they care so much about friendly numbers? This is probably because they put such a heavy connotation and emphasis on the relationship between numbers. Side note, this is something I ended up reading and thought was just really cool. There was actually discovered a number of rounds where if you add all of these proper divisors, you get this, all of these proper divisors, you get the next one, and so on and so forth. And for the one at the bottom, if you do that 28 times, you get the same number. Completely outside the realm of the Pythagoreans, but I thought that was pretty cool. And I think if they were still around, they would think it was pretty cool. All right, so Pythagorean triples. I'm guessing this looks familiar to you. Pythagorean theorem. So despite being called the Pythagorean theorem and probably being how most of us are introduced to the idea of Pythagoras and the Pythagoreans, we aren't even sure if Pythagoras is the one that came up with it. In fact, people theorize that Pythagoras came across this way of computing triples in Babylonia during his travels. In fact, in Babylonia, these sorts of triples had been being computed for thousands of years earlier. But even then, Pythagoras and his Pythagoreans were the advocates for math, and they were the ones who got it popularized, and as so many times we see in history, therefore they're named after Pythagorean and Pythagoras. All right, so the basics. I'm going to grab a sip of water real quick. So, as all things start, you have to have basic rules. When searching for these Pythagorean theorems, they started to notice some basic patterns. And as we read through these three theorems, I think we can all agree. These are things you probably picked up in middle school, elementary school, and they're always holding true. Sum of two even numbers is always going to be even. The product of two odd numbers is always going to be odd. And this one's a little less intuitive. When an odd number divides its even number, it also divides its half. But, I don't know if you can see it in the red, these theorems, although fundamental and fully true, set the stage for something that the Pythagoreans would probably not be a fan of. Incommensurable magnitudes. So, hopping back to the Pythagoreans' ideals, they believed that number was everything, whole, perfect, counting numbers. In other words, they believed if you have a length and you have a second length, somewhere in the world there existed a third length where you could multiply multiples of that third length and get both of the first two lengths. However, this might not be the case. It is speculated that these incommensurable magnitudes, or numbers that are not able to be expressed as a ratio of another number, it came about in the study of a square. So imagine a square of all side lengths 1, trying to compute the length of its diagonal. And as you might know, probably know, the square root of 2 is the diagonal of that and is an irrational number, therefore breaking all of the ideas that the Pythagoreans held so dear. So, I want to go through a proof by contradiction, showing how the square root of 2 is irrational. So, we have to start with an assumption. We have to assume that the ratio of the hypotenuse of an isosceles right triangle, so think of the slide I had before, to its leg can be expressed as a ratio of two whole numbers, a and b. So we want to be able to set up a ratio using that triangle. And they share no multiplicative factors, so it can't be simplified. We're going to let the leg of the isosceles right triangle equal a. So, the square root of 2 over 1 equals a to b. That's setting up a ratio, so the diagonal over the leg, where b does not equal 0 and a and b are relatively prime. If we square both sides, we get 2 equals a over b squared. If we move b to the other side, we get a squared equals 2b squared. The number a, then, referring back to our theorems, cannot be odd, since an odd times an odd is an odd. Therefore, a must be even, or a equals 2c. If we let a equal 2c, b must be odd. Let's substitute this in and keep going. So, then we get 4c squared equals 2b squared. If we divide by 2, 2c squared equals b squared, which shows that b is actually an even number. A number cannot be both odd and even, so square root of 2 cannot be expressed as a ratio of two irrational, since therefore irrational. In other words, since we showed that b is even and b is also odd, our assumption must be wrong because we came up with such a contradiction. This idea might have been the demise of one of their fellows. You might have heard of this legend, but Hippias of Metopontium, an early Pythagorean leader, is said to have discovered these incommensurable magnitudes, been able to prove it, and was promptly tossed overboard by his fellows Pythagoreans for blasphemy. Again, we don't know if that happened, we don't know if that's true, but it's one of the most well-known stories, so I had to include it. All right. So, even with the undeniable existence of these irrational numbers like the square root of 2, there were so few of them discovered and proven, they likely didn't cause too much of a crisis for the Pythagoreans because they did continue to exist after all. So, even though the Pythagoreans didn't disband over this issue with their basic thoughts, it did set up a bit of an issue for one of their ways to compute areas in geometric forms. They used to compute geometric shapes by taking a shape, slicing it, and then moving it. However, if irrationals exist, shapes are not discrete. Shapes are actually continuous. So you were not guaranteed to have the exact same area if you were to slice it and move it. They had to come up with a way to calculate areas, volumes, and lengths by not cutting and moving these shapes. They ended up coming up with an application of areas method to solve this problem, and this led to geometric algebra. So we know base times height equals the shape equals the area of this. That was kind of the beginnings. Figurate numbers. It is thought that these shapes were actually represented in the sand with pebbles, which is a big deal because the Greeks were mainly oral teachers. They didn't want to write anything down. They wanted everything to be communicated orally. So writing it down and doing it in the sand was a big deal. Numbers end up being classified by the shapes they could form. So 1, 3, 6, and 10 are classified as triangular numbers. Square numbers 1, 4, 9, 16, pentagonal numbers. And I'm sorry, I couldn't find an actual slide. They actually had rectangular numbers instead of hexagonal numbers. So imagine a square shape, but with an added line. So it's not a perfect square, instead it's a rectangle. This led to series. So here I have way more than the 4 figurate numbers that the Pythagoreans dealt with, but I thought it'd be interesting to look at it anyway. So triangular series, they were able to come up with a way to express an nth number, figurate number. And here are some of the formulas for that. So if you plug in n, you get that specific figurate number. So what? Why does this matter? Does anybody care about this? Later on, in 1665, Blaise Pascal, I don't know if you've heard of the Pascal triangle, had a conjecture. He said that all positive numbers are the sum of 3 or less figurate numbers. So if you take any of the numbers computed here, any 3 of them, 2 or 1, you could create any number in the world, any positive whole counting number. Carl Gauss in 1801 proved this conjecture, and it's still worked with today. All right, Polyhedra. The Pythagoreans were also not obsessed with, but very interested in these shapes. Again, this is an example of how we don't really know exactly what happened. Some say that Pythagoras was able to construct and make all 5 of these polyhedra. Other sources say he was only able to make the tetrahedron, the octahedron, and the dodecahedron. In fact, the discovery of these shapes is also a bit confusing. We don't know if it was Pythagoras, Hippias, the guy who supposedly got thrown overboard, or Theaetetus, one of Plato's successors, that discovered these shapes. Why did they care about polyhedra? There are several theories. I couldn't find a pentagonal iron pyrite, but here I have a hexagonal and a square-faced polyhydrate. Iron pyrite, sorry. There might have been minerals in the area with these faces, with these shapes that they wanted to deconstruct and understand. Remember, their goal was to understand the physical world around them. That's one theory. Another theory is that a non-Italian sect of the Pythagoreans were able to carve a magical object out of soapstone in the shape of a dodecahedron. This might actually explain some of their interest in the pentagram, because if you look at a dodecahedron, you will see the shape of a pentagram. And again, they used the pentagram to symbol that they were part of the Pythagoreans to other Pythagoreans. Their secret symbol. All right. So that brings us to the theory of special means. It is said that within about 500 century span, they discovered 7 types of means. They know for sure that the Pythagoreans, the early Pythagoreans, knew at least about these 3 means. So they had the arithmetic mean, which is the mean that most of us are probably most familiar with. You add 2 numbers, you put it over 2, bam. There's also a geometric mean, where you multiply 2 numbers and then take the square root. And then the harmonic mean, where you multiply 2 numbers, multiply by 2, and then divide by their sum. It is said that Pythagoras might have not come up with the arithmetic mean in on his own, but instead got it from Babylon. And interestingly enough, shapes can be harmonic. If we look at the cube has 6 faces, 8 vertexes, and 12 edges. Therefore, this means that a cube can be a harmonic body, because if we plug in 6 faces and the 12 edges, we get 8, which fits the harmonic mean. All right. They also believed that music is number. Remember, music is one of the areas that they studied. Legend goes that when Pythagoras was walking past the blacksmiths and heard the ringing of different sized hammers on steel, he was struck by the realization that math was music too. So, imagine you have several strings, so the 6, 8, 9, and 12-inch strings, and you could vibrate all of them, so stretched out. An octave would be the sound of the 6th string to the 8th string, so the proportion going from 6 to 12 equals the original string length. A fourth would be plucking the 6th string and the 8th string, or the 9th string and the 12th string. Because if you look at 6 to 8, the jump is 2, which is a fourth of 8. And from 9 to 12, 3, which is a fourth of 12. Same idea goes for the 5th, and the major tone is a jump from one to the other. Again, we don't know if this happened, but we do know that they had extensive research into music. They would set up string tables and pluck away, and they built their own tuning system, but as you go through the system, you actually get slightly more flat, so current music has switched to a less Pythagorean-based system. And as all great things do, the Pythagoreans did eventually fall. Remember that Pythagoras was a very political entity, and some political things never go well, as we know nowadays. The same aristocrats that had once used the Pythagoreans as an example against democracy because their hierarchical structure worked so well, turned against them and drove them out of the city. So they got chased away from their homes. They ended up in Mesopotamia in about 500 BC. Pythagoras ended up dying there. And when a dramatic revolution swept through the city, their homes and cities were burned to the ground. After Pythagoras' death, the Pythagoreans split into 2 societies, the mathematikoi and the alismatikoi. As you might have guessed, we don't know much about the alismatikoi, but the mathematikoi grew and blossomed and became the first theoretical mathematicians. They are the origins of the word mathematics and mathematician, and are largely responsible for the maths we have today. And I have a question for you. Do you think you can make it as a Pythagorean? And that is all.